develop and repurpose usable, consumable energy through fossil fuel, uh, hydro, solar, nuclear, it goes on and on. With all the research for the gravitational waves, it's measuring massive energy. Is there an opportunity, hopefully in our lifetime, that an aspect or characteristic of the research might be able to be harnessed or repurposed to produce consumable, usable energy, to our homes and businesses?
So, luckily for us, well, okay, so gravitational waves, as Einstein told us, are generated by very massive objects. So to produce enough significant amount of energy, you need black holes. To give an example, the Earth moving around the sun does generate gravitational waves. The entire Sun-Earth system produces about 200 watts in gravitational waves. So way less than one single lamps in this lamp. So we really need gigantic black holes to produce a lot of energy. Luckily for us, I would say there are no gigantic black holes nearby. So will there be an application in the next decade or 2 decades of gravitational waves? Let me expand the question. What is the practical application of all of this? I don't know. Probably nothing today, probably nothing in 20 years. Almost certainly something in 100 years. Because think about it, 100 years ago, Albert Einstein was sitting in his office and decided to understand how gravity works and produced this fantastic theory, which is the general relativity. Today, you to drive here, you probably punch in the address of this place on your smartphone and use some maps to get here. That relies on GPS. The GPS technology would not be possible without our understanding general relativity. Was Einstein thinking about GPS and navigation? I don't believe so. So, what are the implications of fundamental science in 100 years from now? I have no idea, and that's the beauty of it. It will be something fantastic, I'm sure. What? I don't know. Come back 100 years, ask me. Yeah.
Can you talk a little bit about how the radio waves emitted from pulsars help inform our reading of the gravitational waves?
Yeah, so pulsars are called pulsars with a pulsate, right? Because they are these spinning balls of neutrons that have a very strong magnetic field, and so they produce beams of radiation, radio waves mostly, that goes out along the axis. As they spin, this thing behaves like a lighthouse, right? If we so happen that we are in the path of this beam sweeping around, we see them pulsate. So that's one way we have detected a lot of pulsars. That tells us exactly where they are and how fast they spin. So that allows us to predict exactly what frequency the gravitational waves should be. So that's why we do targeted searches. So we know that the Crab pulsar spins at about 30 times per second. The additional waves will be emitted at double that frequency. So we are looking at 60 Hz to see if there is a gravitational wave signal there. The Vela pulsar is about 21 Hz, so we look there. So there are thousands of known pulsars that are observed in electromagnetic waves, and that inform our searches for gravitational waves. We haven't seen any yet. Another one, I don't know what's for.
So, how far do you see with a 40-kilometer Ligo, and how is it that you can go 40 kilometers between zero and the end of the Big Bang?
Yeah, so right now, how far we can detect gravitational waves depends on what objects are producing them. So, for the collision of two neutron stars, our detectors can get as far as about 160 to 170 million parsecs. So a parsec is about 3 light years. So we used to think in parsecs, like for astronomers. So that's how far you get for these stars. For black holes, since they're bigger and they need stronger gravitational waves, you can go farther. So we get to 3 to 4, maybe 5 billion with a B, parsecs. So that's as far as we get now. And the effect of gravitational wave is proportional to the size of your instrument. So by just making it bigger, you almost automatically increase your sensitivity. That's why someone said, well, what's the dumbest possible way to make it more sensitive? You make it bigger. Of course, it comes with a lot of problems. For example, if we were to use exactly the same steel that we use today for the vacuum pipe, and you'll see a piece of the pipe later on, the cost of the steel itself would be the major cost of the entire project. And we're talking about $1 billion in steel. So we have to figure out way to make it cheaper. So it might seem as simple say, well, you know what you're building, you just build it bigger. Sure, yeah, but unless you have $1 billion for us to use it, then it's better for. And even if you had $1 billion, I would rather invest that on more advanced technology rather than using raw materials, right? But
All right. So you're measuring the waves that are propagating through like fabric of space-time. You're using like the ocean and stuff. So it's like what there's like a responsiveness, or like it wants to go back to flat in between the signals. And so I was wondering what are you learning anything new about the properties of the space-time itself that's actually like deforming via the waves and things like that?
yeah, so space-time is an extremely rigid medium, if you want. So it's not very pliable, and that's what makes gravitational waves very difficult to detect. So in some sense, every time we detect a gravitational wave, we compare the signals we detect with our prediction, or the best prediction from having measured the size, the distance, etc. So the prediction is based on our understanding of how gravity works. So as of now, we are able to tell you that at the level of 1% or better, our prediction matches our measurement. So that means that space-time behaves exactly as expected. It's a very rigid medium, doesn't have any memory, the gravitational wave passes through all these kind of ideas, right? So at some point, hopefully we will see that the measurement, the signals we get from collision to black holes, those signals don't really match that well what we predict. That's when things will get exciting. Then that's where it means that our understanding of the universe is flawed, and that will give us an idea of what is the next big thing to discover, to learn.
Following up on what you were saying about the difference between predicted and the observed data, and you had a slide where you showed that you could curve fit it to determine the age of the signal or distance of the signal. In that slide, it shows a very spot-on match, but not perfect. Are the imperfections, do you think, because of instrumentation limitations, or because there's background noise or thermal noise in the circuit?
So those imperfections in the signal matching are all noise in our detector. It's like when you tune your radio, you drive up out in the mountains and your radio is tuned to the station with some static background noise, right? That's what happens. So what is limiting the noise of our detector is all kind of very much terrestrial noises. Low frequency vibrations. We have very sophisticated vibration systems, but still, Earth, everything's vibrating, traffic, micro earthquake, all of that. The Brownian motion, the vibration of the atoms themselves, because they're at higher temperature, that's a big source of noise for us, so we're trying to improve that. Even the fact that lasers are quantum objects, they're made of photons, and that means there's some uncertainty, quantum uncertainty in our ability to measure how many photons there are. That's another source of noise. So all those wiggles you see there, they're not noise out in the universe, it's noise in our own instrument. So my job and the job of my team is to make that noise smaller, smaller, smaller. It's not always the easy.
And you said now the focus will be on something in the 60 hertz range. Good thing we don't have much 60 hertz background noise.
Yeah, I know. It's kind of unfortunate that the pulsar, the crowd pulsar is almost exactly there. Yeah, that's not. It's a 62, I think, which is far away, but still.
Yeah, a little something.
Yeah, you just have to work with. Yeah. Okay. You?
You mentioned that for the building on 2/3 of the data has been released or parsed through. What type of data volumes are you talking about for these sectors, and what type of infrastructure goes into managing and using that data?
Yeah, so our detector produces about, if I remember correctly, 80 megabytes per second on each one. To give you an idea, that's equivalent of streaming 100 high HD movies at the same time. So it's a lot, but it's not crazy lot. But still, sifting through all that data continuously to look for gravitational waves is quite an intensive job. So we have dedicated, cosa io dirlo, Medina, come in? Come on.
How much more do you get? We get you.
Oh, but I want you to answer some questions too, just in case. So we have dedicated computers, dedicated computer clusters, and the data analysis pipeline, as we call them, there are all code that has been developed and written by our scientists and engineers to be able to handle that amount of data. It's about 80 megabytes per second, each domain, yeah. Okay, back there.
The question is, in the gravity wave, also the dark matter, is in that wave, is it possible in future to harvest dark matter?
So dark matter is one of the big mysteries of the universe, right? So we believe we need dark matter because we look at galaxies and we see that the way the galaxies spin does not match the amount of bright matter we see in the galaxy. So we need the gravity of dark matter. So for a while, there was this idea that, oh, well, what is dark has a lot of mass? Black holes, fantastic. So maybe dark matter is with black holes. Unfortunately, that didn't quite work out because if there were black holes, they would you would see them. So at some point, a star would fall into one of those black holes, or would be passing behind the black hole. The black hole will behave as a lens and magnify the star. So we have looked for that, and we didn't see it. So maybe gravitational waves might be able to tell us something about the dark matter, because at the end of the day, we are measuring gravity, and all we care about that dark matter is that it's gravity. But it's very likely that dark matter, the best candidate today is some sort of heavy or light elementary particles that are diffused almost everywhere. So if that's the case, they should not generate gravitational waves. But hey, maybe we'll be surprised. Yes?
So as sensitivity increases, I imagine you'll start to have overlapping, like multiple gravitational waves. And is there kind of a danger that it's just going to end up in noise because there'd be so much overlap?
Yeah, so funny you mentioned that because, well, first of all, me and my team as instrumentalists, our job is to make the instrument more and more sensitive, which means make the life of data analysis people harder and harder. Probably that's why they hate us, but no, maybe they don't really hate us, but you know. But yeah, eventually we will get to a point where two signals will overlap each other. We believe that Cosmic Explorer, the 40 kilometer long detector, when it will be at full sensitivity, in the most sensitive band, we'll have what we call confusion noise. So many signals from binary systems out there that will be too hard to disentangle all of them. It will look like a background noise. But even if that's a noise, yes, but it's a noise coming from the universe. So it contains a lot of information about what's going out there. So it's still a very interesting thing to be able to see. Okay. All right.
I have a couple. One of them might be better for once we get academics about the newsletter specifically. But the other thing is, what can be determined about the collision of neutron stars by the length of the delay between the gravitational waves and the gamma rays?
So as I mentioned, gamma rays took about 2 milliseconds to.
Is it always 2 seconds, or is there?
Well, in this particular case, it was 2 seconds, and then astrophysicists used that information to model the density and the size of this cloud of gas around the stars. You can imagine that's a very difficult model to do, because first we don't know. We can't go in the lab and measure the properties of a piece of neutron stars, like we can go in the lab and measure properties of a piece of steel, right? So we have to kind of guess. So actually, this collision was the best observation as of today to determine the properties of that matter. So this little delay rules out particularly some model from is the neutron star matter very stiff or less stiff, all of that. So I don't know much of the details, but this gives you the kind of idea, right? From data delay and other information, you can say how big is the cloud of gas around it, how dense it is, and that tells you something about how neutron stars behave.
And then as far as the beam splitter goes, I was wondering because it hits from one side and it reflects, but when it comes back, then it passes through.
It reflects on the other side too, right?
Right, but as it goes through the detector, it's not reflecting back to the laser again.
It also reflects. So most of the light goes back to the laser, and only a little will leak to our detector if there is a gravitational wave.
Right.
That's one of the reasons we have that power sighting mirror. Because if you think about it, you're sending a lot of laser power into your detector. You have the beam splitter. Nothing goes out this way. Nothing goes out at the end. Almost comes back toward you. So it seems a month idea to put another mirror here to reflect everything back. So that's what we do.
I see, so the amplitude discrepancy is. Right?
So you have to make sure that you maintain the distance such that the laser reflected back there again interfere constructively with the laser interferometer and then gives that.
Okay.
You have a question?
I did, but it was similar to that one. I just had wanted to know, you said the gravitational waves and the light, they don't occur at the same speed, but they're a few seconds apart, but it's actually gamma rays, not light.
It is light, because
It's
gamma rays
it's
is light.
light.
Yeah. So they do travel at the same speed as far as I can detect. It's just that the photons took a longer time because they were continually. So light and gravitational waves travel at the same speed in vacuum.
Okay.
But light going through dense matter is slowed down a little bit, so the photons are bouncing around.
Oh, so that's what causes.
That's what causes this
Oh,
that delay.
thank
Yeah.
you.
Okay, two more questions. One in the back.
Yeah,
Maybe three.
if you have a more sensitive detector, would you be able to glean some information on what the wave passes through? Because I imagine as it passes through other particular massive objects that might deform space-time themselves, the wave might deform it on its way to Earth.
Yeah.
So would you be able to tell something about?
Yes, absolutely. So we have some hints of an effect called gravitational lensing for gravitational waves. So gravitational lensing has been observed for light. So we see these Einstein rings or Einstein crosses, right? That is the same as that object, where you have a big galaxy and an object behind, and then you see multiple images because this big object deforms space-time and the gravitational wave of this object acts as a lens. So we haven't quite observed definitively that with gravitational waves, but we have some hints that that's happening. So we expect that eventually we will see essentially what happens, two gravitational wave signals that looks very similar, and when they arrive at a slightly different time because they went two paths around the big object. So we expect to be able to see that. There was another question here, I think, yeah, second to last, and there's another one there, and that's all. Right.
I have a question about the presentation slides you had. It was, two heavy objects orbiting each other in emitting waves. They look like they create a shock wave behind them and create a ripple. I wouldn't expect a shock wave because the gravitational waves are much faster than the speed of the thing. Can you talk about it, like how conceptual versus real was that?
That is what
illustration.
So what that illustration there was an actual real generative simulation. So that's a real representation of what happens. So what you see is not quite a shock wave, but you see the two objects moving faster and faster and faster. And so gravitational waves escape at the speed of light much faster, yes. The two objects are orbiting around each other maybe 100 to 1,000 times per second. And so you see ripples that are faster, faster, and faster. Eventually they collide, they create one bigger object that is still vibrating and sheds a lot of energy in vibration. So it's not quite a shock wave, it's just faster and faster ripples.
So each one of those ripples that kind of like aspire, like was an interference pattern from
No, it's really you don't see interference really. Every time the objects go one orbit, you see gravitational wave oscillation. Then they go away. But it just looks like interference pattern because they get faster, faster, and faster. But it's actually just the orbital oscillation. The gravitational waves follow pretty closely the orbital motion of the objects. Very last question.
Okay. Last question. It's kind of two, but have you seen any abnormalities in your observations, and how rigid is the protocol in your like engineering? Because have there been any happy accidents or anything like that that helped out?
So we have not seen anomalies in our data that we couldn't explain by some local disturbances or anything like that. So we have routines and ways to check if the gravitational wave signals we see matches what we expect from prediction, and we got into 1% or better than that. Part of the limitation is the sensitivity, part of the limitation is how well we can calibrate our instrument. In terms of happy things that happened, if you want, the very first detection happened about 2 to 3 days before we were supposed to start observing. It just happened that our instruments were working, and people that took observatories were tired at night and said, enough commissioning, enough work in the instrument about today, let's just go home. When we go home at night, we just flip a bit that says the instrument is undisturbed. So that data is good. And one of the first nights we did that, even before the official started the run, the first gravitational waves came through and we detected it. So That was a very nice speech from Bench, I guess. Okay, there will be a lot of time for more questions. Now, for the tour, we have 4 people here that will introduce themselves during the tours. So the 4 of them and myself, we make sure to divide you in 5 groups, more or less the same size. And we have 5 different stations. So please remember, meet one of the leaders and remember them and follow them. They will take you to the different location of our labs. Because as I mentioned, we don't have the gravitational detectors here, right? But we have all the engineering and all the research. You can actually see some of the parts much better because they're out there on the table rather than in the chambers. So we will all go to the same places, and you will all have the same explanation of things. Feel free to ask as many questions as you want. Everyone is very knowledgeable and knows a lot about LIGO, and all of them have different expertise, so you might learn some different things. So if you have a couple of friends, split up if you want, so you can learn a little more and discuss later. Joe, how are we going to do this?
Guess we can just take them, might as well take it by rows.
Okay.
Start in the front.
All right. Let's. So how many people do we have?